Lab 15 is much like Lab 14, using many of the same equations. In both labs, we discuss ways in which we can determine distance to far-off objects just using observations we can make from here on planet Earth. In Lab 15, we'll be looking at a measurement called redshift that we referenced a little bit back in Unit 3. Here you see a set of spectral lines of the quasar, a distant active galactic nucleus. Specifically, we're looking at this double line. The rest of the spectrum is irrelevant for this lab. Using the partial scale here, estimate the wavelength of this double line, what wavelength value in angstroms this is. Then note that this value has shifted significantly from its normal position of 1,215 angstroms. Use the equation to determine the redshift value z, recalling that delta lambda, again, is the change in wavelength from where the spectral lines are to where they ought to be, and that lambda naught is the original normal position of that particular wavelength. You'll now use this equation to determine velocity. The equation is given in terms of velocity over speed of light. And notice that your question is asking for velocity alone. So you just have to multiply the c over to the other side to get the v alone. Plug in the z value from number 1 into this equation and solve for this fraction of the speed of light. Then, using the given speed of light, solve for the velocity in kilometers per second. Then, for number 3, you're going to use the book's given value for h and the velocity you just found to solve for d, the distance. Be super careful with your units. If you notice that your velocity is in kilometers per second and your h is in kilometers per second per mega light year, when you solve for d, it will come out in mega light years, or millions of light years, and you'll have to divide your answer by 1,000 to turn it into billions of light years. As a check here to verify that your answers so far are reasonable, notice that the value here cannot be more than 1, as nothing is faster than the speed of light. And the value here should be something close to the age of the universe in billions of years, as these quasars are among the most distant objects we can see. Now on to your final 2 problems of this course. Before beginning number 4, we will have to make one final conversion, as the equation used in number 4 requires the distance to be input in number of parsecs. You'll need to take your last answer value in numbers of billions of light years, divide by 3.26 to turn billions of light years into billions of parsecs, then multiply by 1 billion to get the number in standard form, and it will be a really big number. Then, for number 4, you'll have to use the distance modulus formula, this equation with the log in it, to solve for absolute magnitude. You're given the apparent magnitude here, and you have the distance from the previous problem. Solve the right side of the equation first, then rearrange what is left to solve for big MV. Finally, given that the absolute magnitude of our entire Milky Way is -23, use this equation to compare the Milky Way's magnitude of -23 to the magnitude of the quasar you just found. This expression will give you L, or the luminosity of this quasar. This value should explain why we're able to see this quasar even though it is so very far away. When this lab is successfully completed, you are done with this course. Congratulations. As always, if you have any questions as you go through this last lab, let me know. I'm always here to help. Good luck and congrats again on finishing the course.